Okay friends, let's welcome to the online course on signals and system. Let's see what is the subject we are discussing here. The subject is signals and systems. So in this signal system, today we are seeing the subject which is topic. The topic what we are discussing here is fundamentals. Okay. Before entering into the subject, let's talk about the subject and why we are required to see this subject as a primary subject. Okay. So let's see. Before starting this subject or before saying anything, I want to say one thing, that you require nothing here to understand this subject. That means you don't have to remember or you don't have to know something which is before this. Means prior knowledge is not at all required for this subject. So you can start from the scratch, that means 0 level. Then you can go to up to a higher level. That's what the subject means here. Okay. So here so many people will ask what are the books we have to go for. I will simply suggest the book is Signals and Systems by Oppenheim. By Oppenheim. So this is the book you can prefer for the knowledge of subject or for the theory part, and you can see so many problems so which are repeated in the GATE examination also or in so many PSUs also. And another one is RK Kanodia you can use for the practice purpose. That's all one way to say, for the practice purpose. And mostly go through previous questions. This is the one thing. And previous papers, whatever you are preparing for. So if you prepare for, let's say, GATE, go through previous EC, electrical as well as instrumentation papers, so that you can understand what to study, what not to study. That's the one thing you can understand. And previous IES questions, previous Transco, Genco, and previous ISRO, and these things you can follow. So that's what is going to give you insight how to prepare for the examination, what you are preparing for. Okay. So this is about the books what we are going to prefer. Let's see what are the topics we are going to see in this topic, in this signals and system. Topics. The first one is basics or fundamentals. Second one, this is a classification of signals. Third one, classification of systems. third one, fourth one, that is in the special case, that is LTI system. So these are the four topics which we have to understand thoroughly before entering into the next advanced topics, because these topics are like a fundamentals for us. Okay. Next, fifth one, Fourier series. Sixth one, Fourier transform. Seventh one, this comes in the Fourier transform itself, which is a sampling theorem. Sampling theorem. These are the topics. Next, seventh one, Laplace transform. Laplace transform. Next, Z-Transform. In this Z-Transform, we will see the realization or synthesis, of discrete systems. Sometimes they will call it as a digital system also. Discrete system. Once we complete the Z-Transform, so up to this 8th chapter, so these topics are common for everyone, that is EC, EEE and instrumentation. So this is up to electrical. Up to this topic, electrical people has to study. After that, no need for electrical people. But after this, we have to see for those people who are from EC background and instrumentation background. So next topic, that is DTFT. Next, DFT and FFT. Next, filters, digital filters. So these are the topics what we have to discuss in the entire signals and system course. Okay, please take a note. These topics only for EC and instrumentation, not for electrical people. Okay, just make a note. What are the topics we are discussing? What do you mean by signal? So if I ask the same question, what is a signal? Then you can give so many answers. Signal is this one, signal is that one. Okay, but let's say define. How we can define a signal in a more fashion, or everybody can understand what is that signal definition. First, listen. Signal. What do you mean by signal? I can say signal is a function. We know functions. What do you mean by functions? Which is nothing but mapping. Suppose if you know one variable, so on that variable, depending on that, we are having some other variable which is going to keep on varying. These are called as functions. So I can simply say signal, mathematically we can say it as like a function of one or more variable. So suppose let's write the definition first. What do you mean by signal? Signal is a function of one or more variables. This is what the definition of signals, one or more variables. Okay. Then why signals? If somebody is asking why do we require a signal, Y signals. Because they carry information. We require signals because they carry information. Because they carry information. They carry information. So this is about the definition of signal, why we require a signal. So that, let's see some examples you can understand easily. The first example, I can see a voltage signal, simply a voltage waveform. If I say V of t, voltage which is varying with respect to time, let's call it is a sine 10t. How we can draw this? Everybody knows it. How we can draw a signal? Time. One minus one. This is a sine wave which is varying with respect to time. So let's see. Is it a function? Yes, it is a function which is varying with respect to time. So how many variables we are having? Only one variable, which is independent variable t. So with respect to time, the signal is varying. Understood? So voltage is a signal, or voltage is a function with one variable which is nothing but t. So this is one example we can say. Next, let's take another example, second one, a photograph. A photograph. What can we say about a photograph? Can I call photograph is nothing but a signal? Of course, it is nothing but a signal. Then what it is showing? So definitely a photograph looks like this maybe. Sir, you said photograph is nothing but a signal. Then what is the variable here? What is the variable which is nothing but independent variable here? Let's see first which one is varying with respect to what. Can I say the color from one point to one point, if it is varying, that is going to create a photograph. So can I say photograph is nothing but a color which is changing with respect to x-axis as well as y-axis. So if I take this is the x-axis, if I take this the y-axis, so the photograph is nothing but function of x and y. What is this function? Which is nothing but color intensity, maybe brightness, whatever it may be. So we can say that. Next, let's say third example. Let's talk about video signal. Video signal. Video, I can call it is a signal because it is carrying some information. Can I say photograph? If this photograph is keep on changing with respect to time, that is going to create a video. That is as simple as that. So I can say video is a function. Video is a function of x-axis, y-axis and time. Means the color is changing with respect to x-axis, y-axis as well as time. That is going to create video. So I can say this is also a function of three variables. Next, another one. Let's say temperature. What about temperature? Temperature is also a signal. That means it is a function of, let's say, from this point, means in this room, if I take one point, if I take another point in somewhere else, definitely the temperature is going to change. So from this, can I say the temperature is varying from point to point? So how can we show point with respect to x-axis, y-axis, z-axis? So from this point to this point temperature is varying means with respect to x-axis, y-axis and z-axis the temperature is varying. That's one way. Next, suppose if I take the same point, at this point I am measuring the temperature. At this time and evening or some other time if I take, definitely the temperature is going to vary. So can I say temperature is also varying with respect to time? So there is also one way to say it. So I can simply say temperature is nothing but a function of the variables x-axis, y-axis, z-axis and time axis. These are the variables which are present in a temperature. So now once we understand what are the independent variables present in a signal, then we have to define one term which is called as dimension of a signal. Let's say okay, let's say dimension. What do you mean by dimension of a signal? So from here itself I will say, suppose voltage signal is a function of one variable which is nothing but t. So I can simply say it is a one-dimensional signal. And let's say photograph, it is a function of two variables which are nothing but x and y. So I can say this is a two-dimensional signal. If I say video, it is a function of x, y and t. I can simply say it is a three-dimensional signal. And temperature, it is a four-dimensional signal. So from this, can you define what do you mean by dimension? Dimension is nothing but number of independent variables present in a signal is nothing but a dimension. So I am writing that number of independent variables present in a signal is called dimension of the signal. So from this, can you tell me what is the dimension here? The signal is a one dimension and photograph is nothing but a two-dimension signal and video is nothing but a three-dimension signal and a temperature is nothing but a four-dimension signal. So this is what the meaning of signal and this is what the meaning of dimension. So remember one thing, in our syllabus we are having only one dimension signals only. So no need about two dimension, three dimension, four dimension. These two dimension, three dimension, four dimension are like they are having more than one variable. They are called as multi-dimension signals. They are not in our syllabus. We are having only one dimension signal in our entire course. So just understand, we can always deal with this kind of voltages and currents which are varying with respect to time. They are nothing but the signals for our course. Okay, let's take this. So once we understand what do you mean by dimension and what do you mean by independent variable here. So mostly we will deal with the independent variable which is nothing but time only. So let's suppose if a signal is a function of time, in that regard, that means based on the information of time, we can divide or we can classify the signals into discrete time and continuous time signals. Okay. First, let's see, based on time information, we can classify signals into continuous time signals, in short CT, discrete time, In short, DT, discrete time signals and continuous time signals. Okay, try to understand what do you mean by a continuous time signal. Suppose let's take one example so that you can understand easily what do you mean by a continuous time signal. Okay. Usually continuous time signals can be represented with x of t. Now try to understand what do you mean by continuous time signals. Continuous time signal is said to be because if it defined for all the values of time, try to understand the word defined and try to understand the word existence. Maybe the signal is existing only for positive values of time, the signal is not existing for negative values of time. That is a different story. Where the signal is existing is not important. But is it defined or not? That means, let's say, if somebody is asking what is the value of the signal at -1, you can simply say the value is 0. If somebody is asking what is the value of the signal at a t is equal to 4 seconds, you can say this is 2. If somebody is asking at 2.5, you can say the value. So at any instant of time, if you want to find the value of signal, if it is possible, then we can say that is a continuous time signal. That means the signal has to be defined for all the values of time. Defined means you have to say at each and every point of time what is the value of the signal. Then I can call that signal is a continuous time signal. So just understand the definition. Signal is defined for all the values of time. Then we can call it is a continuous time signal. Then what do you mean by a discrete time signal? When can we say a signal is a discrete time signal? Usually the notation for it is x of n. Suppose let's say x-axis is n because that is the independent variable. At 0, let's say the value is 2. At 1, let's say the value is n is always integer, remember. Let's say at -1 its value is 1. At 2 its value is again a 1. Okay, let's say this value is 3. Okay, if I consider a x of n signal like this, I can call this is a discrete time signal. What do you mean by discrete time signal, sir? The signal is defined only for particular values of n. In general, that n is nothing but an integer. In our course, n is nothing but an integer. So at integer values of n, only the signal is defined. Sir, what do you mean by that, sir? Let's say, if somebody is asking, can you tell me what is the value of x of 0? What is the value of x of 0? We can simply say the value is 2. No problem. If somebody is asking what is the value of x of 1, you can say the value is nothing but 3. So everything is good. But what if I ask what is the value at 0.5? At 0.5, what is the value? So many people will think that it's a 0. At 0.5, the value is nothing but 0. But absolutely wrong. That is nothing but undefined. So many people may get confused. Let's try to understand this in a different manner. Let's say naturally occurring discrete time signal. One very famous example what we know. is a population. Let's say usually population, let's consider maybe in a March month. If I calculate population March, let's say 2017, let's say we got 100 crores of the population. Next I will go for next year March 2018. Let's say we are having a population of 120 crores, let's say. So definitely this is a discrete time signal. What if I ask what is the population at a point where it is maybe in between, let's say October 2017? Can you say the value is 0? No, that value we don't know. That is undefined value, because the value is defined only for March 2007 and March 2008. That doesn't mean that for remaining values its value is 0. No, we cannot say like that, but we can simply say that value is undefined. That means x of 0.5 value is undefined. That means I can give the signal definition, discrete time signal, like this. Signal is defined only for in this case integer values of n. Means the time axis is discretized. The time axis is discretized because we are taking only discrete values of time. We are not taking all the instants. I am taking only some instants. Then we can call it is a discrete time signal. So I am telling you that I am not generalizing this. In our syllabus we are having x of n. So for that only I am discussing n value must be integer. Is that clear? Okay, take it. Continuous time case and discrete time case. Most people are usually misinterpreting the things like discrete time signal is nothing but a digital signal. No, they are entirely different. Let's talk about another way to classify the signal, which is nothing but analog signal and digital signal. So whatever we have seen the information on the time axis, that means based on the time information we can divide the signal into a continuous time signal into discrete time signal. That is the one way. Suppose if I check the amplitude, that means y-axis information. If I take the amplitude information, I can divide the signal, or we can classify the signal into analog and digital signal. Let's see. Based on the amplitude information, signal can be defined or signal can be classified into a analog signal and digital signal. First try to understand what do you mean by analog signal. If I take x of t signal, which is like this, a sinusoidal function between 3 and -3. If I ask what is the dynamic range of this signal? Dynamic range means what is the amplitudes it can take. What are the amplitudes it can take? That means it can take any amplitude between -3 and +3. That means what is the lower limit, what is the upper limit? What is the lower amplitude? What is the upper amplitude? Lower amplitude is -3 and upper amplitude is +3. So the dynamic range is -3 to +3. -3 to +3. Next, I will give you a definition why it is called as analog signal. Before that, let's see a digital signal. Digital signal. This is also another x of t signal with respect to time only I am defining. Okay. So this is called as digital signal. Here also the dynamic range is nothing but -3 to +3 only, because it is taking the lowest value is -3, highest value is equal to +3, and let's call it is 1, let's call it is -1. So here also the dynamic range is -3 to +3 only. -3 to +3 only. Dynamic range is -3 to +3. I am writing completely. Dynamic range is -3 to +3. Then why it is called as a digital signal? Why it is called as an analog signal? Try to understand. If the signal is defined continuously or a discrete time, it doesn't matter, but it takes all the values between -3 and +3. That means if somebody is asking how many values are there between -3 and +3, they are infinite. It can be any value, -2.9999, like that, 2.8, 2. Like that. So it can take any value between -3 and +3. That means it can take infinite values. So analog signal, that means in the amplitude wise, it can take any value between -3 and +3. Means the amplitude can be any value in the dynamic range. Then we can call this is the analog signal. Whereas if I take the digital signal, still the dynamic range is -3 to +3. But is it taking every amplitude between -3 and +3 like infinite values? No, it is taking only particular values. It is taking 0, it is taking 1, it is taking 3, -1, and I can say -3. These are the only values it is considering, like 5 values. Let's say 0, 1, 3, -1, -3. These are the only values it is considering. It is not considering the remaining values. That means dynamic range, even though it is same, but what are the amplitudes it is considering? So I can say it is a digital signal. So let's see. Continuous in the amplitude is a analog signal. Discrete in a amplitude is called as digital signal. I hope you understood. So it can take all the values or all the amplitudes within the dynamic range. Within the dynamic range. Whereas digital signal, it can take only particular amplitudes within the dynamic range. Then we can call it is a digital signal. So in general, if I write like this, continuous in time, it is continuous time signal. Continuous in amplitude, then we can call it is a analog signal. Next, discrete in time is a discrete time signal. Discrete in amplitude is a digital signal. Remember. Okay, make a note. So based on the time information, it is a continuous time and discrete time. Based on the amplitude information, it is analog and digital signal. The well-known example for digital signals is a 0, 1 binary. Okay, so in the binary, if you observe carefully, this is also a digital signal. Why? Suppose for a time period is 0, maybe 1, maybe 0, maybe 1, like that. 0, 1. So the dynamic range is only two values, 0 to 1. But 0 to 1 we are having infinite values actually. Suppose if somebody is asking between 0 to 1 how many values you can take infinite values. But instead of taking infinite values, it is taking only two values. What is nothing but 0 and 1. So out of the dynamic range, it is considering only two values. Then what kind of signal it is? Definitely a digital signal. Understood? So here dynamic range is 0 to 1. 0 to 1. But it is taking only two values, which are nothing but 0 and 1. So definitely it becomes a digital signal. Okay, take it. This is what you have to remember. Finally, the observation part.